Hello everyone, welcome to the lecture series on fundamentals of generative AI and large language models. We are in the week 2 and so far we have seen the working mechanism of autoencoders theoretically. In the previous session we have seen mathematically how exactly autoencoders works. We have seen the reconstruction laws both for mean square error as well as the binary cross entropy. That is, if you are using an the real valued features, then if the input is real valued features, then we will be using a mean square error. If the input is binary, then we will be using a binary cross entropy. In this particular session, we will be seeing with the different types of autoencoders. More specifically, we will be focusing on CNN based autoencoder. Then we will see something called as a shallow autoencoder and a deep autoencoder. Now, why is that? We are first starting with CNN is in the previous session, in the last two sessions when we saw the theoretically and mathematically autoencoders, we had taken tabulated data, that is where the encoder and decoder were implemented as multi-layer perceptron. Now, what if their input is an image? Then how the given input image, how the model is going to reconstruct it. So, if an input image is image, if our input data is an image, then it is a CNN based autoencoder. So, how exactly CNN based autoencoder works? So, we know that irrespective of whatever may be the data, if it is an autoencoder, we will have an encoder, we will have a latent space and we will have a decoder. So far encoder and decoder were of multi-layer perceptron because of the input data. But now since the input data is an image, so the encoder has to be in CNN based. So go back and then recall from our week 1 session. So in the week 1 towards the end of the week, the last two sessions were on CNN. So we had done the revision there because it will be useful here. So we know that in CNN the different components are, we had convolutional layer, then we had activation function ReLU, then we had a pooling layer. So if you look into this, convolutional layer is mainly responsible for extracting the features and pooling layer is responsible for reducing the dimension, spatial dimension. So here also, because it is an autoencoder and the input is an image, now at an encoder side we are using a convolution layer and we are using a pooling layer. In the pooling layer, again we have seen from our week 1, we have different types of pooling. It can be an max pooling, min pooling, average pooling, but in autoencoder more specifically we will be using an max pooling. So working mechanism, all that you can once again recall from our unit 1. Then you can get back to this particular session. So here we have an encoder. Encoder uses a convolutional layer and it also uses the pooling layer. In the pooling, more specifically max pooling. And what is that it is responsible for? Because ultimately you see encoder has to extract the most important features and reduce the dimension. That's a latent space, right? The output of convolution will be a latent space or latent code. So how it is possible? It is possible only with convolution layer and the pooling layer. So that is the architecture of encoder. Uses convolutional layer and pooling mainly to reduce the spatial dimension while extracting the features. Next comes the latent space representation or latent code. What is this? This is the output of the last convolution layer in our architecture. So whatever is the output of last convolutional layer will be the latent space representation. So here the output of convolutional layer here in the encoder serves as the compressed representation. That is the representation, a smaller representation where the most important features are represented. Then this latent space is passed to an decoder. So far decoder was a multi-layer perceptron. Now decoder cannot be multi-layer because we have an image as an input. So the decoder has to use the transposed convolution, or we call it as a deconvolutional. Mainly why? Because ultimately the aim of a decoder is to reconstruct the data back. So which means if our input is of dimension 28 to 28 1, so the latent space will be definitely of smaller dimension. Here you see the latent space is of 7 cross 7. So when you pass it to a decoder, decoder has to reconstruct back. So which means it has to give back to 28 cross 28. So which means decoder has to do an upsampling of data so that it will match to the original input. So what we are discussing is CNN based, and in CNN based autoencoder, input is an image, and at an encoder we are using convolution layer and then the pooling layer. At the decoder side we are using a transposed convolution to upsample it. So let's take an example here. This is an architectural diagram of an CNN based autoencoder. If you see here, there is an input which is of dimension 28 28 1, and what is 1 here is a channel, which means we are considering an binary image, and 28 to 28 is the dimension, which is height and then the width of the image. So that is the input that we have considered. That is passed to an convolutional layer. So conv 2D, because we are implementing this in Keras. So in conv 2D, so go back and then recall from our week 1. So in the CNN, what is that we will be passing? We are seeing how many such kernels we should take and the size of a kernel. So here for a convolution operation to perform, the number of kernels are 64 and the size of each kernel is 3 cross 3, and the activation function used is ReLU. And remember this concept, padding equal to same, which means we are applying padding. So when we apply padding, whatever is the dimension, you will be retaining the same dimension towards the end of a convolution operation. So padding is the same. For this we are passing an input. What input? 28 28 1. So the resultant is given to this particular variable. So what will be the output here? The output, since padding is used 28 cross 28, how many such filters we have used? 64 such filters we have used. So that is the output we have obtained. Now that is passed to a pooling layer. So what is pooling? Pooling will always reduce the dimension. So here for a pooling we require an window size. So here the window size is 2 cross 2. Because the window size is 2 cross 2, definitely the input will be reduced by half. So input is 28 28, that is reduced by half, which is 14 cross 14, and 64 will remain the same. So this is the output of the first convolution layer. When I say convolution, here it is both convolution as well as pooling. So that is given to this particular variable. Now that entire is again passed to a second convolutional layer. So what is the input that you are passing? It is 14 14 64. So that is passed to an second convolution layer, which has 128 kernels. Each kernel is of size 3 cross 3. So since padding is the same, whatever the input you are passing, the same input. So 14 cross 14, but here number of kernels are 120, filters are 128. So that's what we have obtained here, and that is passed to a pooling layer. Next is pooling. So in a pooling, again we are using a window size 2 cross 2, therefore you are reducing it by half. So 7 cross 7 into 128. So now that is again passed to a convolution, because what is the latent space? The output of the last convolutional layer. So again you are passing as an this is passed as an input to this. So in this convolution we are using a 256, padding the same. So the filter the input is 7 cross 7, but instead of 128 you have 256. That is what is this, right? So and this entire is a convolutional function, a convolution operation. So you have defined this under a function conv underscore autoencoder. This is an input encoder that we have seen. So since the input is an image, encoder will have convolution and then the pooling layer. That's what we have seen it. Now, what is the latent space? Latent space is always a compressed representation of an input. Input is 28 to 28. By the time we came to a latent space, the input now here is 7 cross 7. Is it not? We have reduced from 28 cross 28 to 7 cross 7. We have reduced it. Now our latent space dimension is 7 cross 7. And how many is such? 256. Now, this is passed as an input to a decoder. So, when you pass this as an input to a decoder, decoder has to do what? It has to upsample it, because ultimately it has to get the 28 cross 28, it has to give back the dimension same as the input. Now, you are at 7 cross 7. So, now we have to do upsampling. So, now let us understand what is upsampling with a simple example, and then we will come back to the same program. So, what is upsampling? Now, whatever the image that you are seeing here, it is a feature map obtained from a last convolutional layer. So, now let us assume the size here, now you have reduced from 28 cross 28 to 7 cross 7. From this 7 cross 7, you should reconstruct back to 28 cross 28, which means now you have to increase this 7 cross 7 to 28 cross 28. So, how will you do that? Let's take the different techniques that are used for upsampling. One is called nearest neighbor upsampling. I am giving a simple example, later we will connect back to the image. Now, let us assume the x is that is this image. Let us assume it is of 2 cross 2 dimension, which is having the value 1, 2, 3, 4, just for an example to understand what is nearest neighbor upsampling. What is our ultimate aim? From this, you have to increase the size. If you have to increase the size, by how much you want to increase? That is what is this upscaling factor. So, it is a scaling factor. A sampling factor, not scaling, I am sorry, it is an upsampling factor. So, S value is 2. So, because it is 2, how you are going to apply on this? Because it is 2, every of the value should be expanded by 2 cross 2. So, now you see this is expanded by 2 cross 2. This 2 is expanded by 2 cross 2. This 3 you are expanding by 2 cross 2 and 2 cross 2. Why 2 cross 2? Because of this scale sampling factor S is 2. So, you have increased by 2 cross 2. Now, when you increase by 2 cross 2, it is like position, 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 then 2. This is what ideally, right? Now, when you have values like this, in this either you can write 1 or you can fill 0, right? Either you can write 1 or you can fill 0. If you fill all of these values by 1, it is called a nearest neighbor upsampling. So, what will be the output? The output here, input is 2 cross 2 and sampling factor is 2. So, multiply each of this, you get 4 cross 4. So, that is the output 4 cross 4, where nearest neighbor meaning whatever is this value, the same you are going to copy in each of this place. This is the same value is being copied. That is what is nearest neighbor upsampling. Second, now in that you can even put 0, right? So, in that position we can even put 0. If you have zeros in all of these, it is called bed of nails upsampling, or it is 0 insertion. So, is it not? We have increased the size. But there is one drawback of just upsampling a factor. What is the drawback? Is there any learning here? Is there anything that the model has learnt? It is just take the values and then put all those values. So, or put 0 values. So, in this particular method, there are no learnable parameters. Although from 7 cross 7 you are increasing to 14 cross 14, just an example. So, there is no if you take a matrix of 7 cross 7 and if you have a scaling factor 2, then you will have an resultant 14 cross 14. So even though you have increased, but you have just increased without any learnable parameters. There is nothing to learn here. So this is not a good approach for upsampling. Then you have a second method. What is the second method? That is called a transposed convolution operation. What is a transposed convolution? Take the input here is 1, 2, 0, 1, and then we will be requiring a kernel. So what is that kernel value? The kernel value is, it is just one kernel value which we have taken it as 2 cross 2. What is a transpose convolution? You take the input, multiply it with kernel. So how is that you do? So and what will be the output size by doing this? Because our ultimate aim is to upsample, which means you have to increase the dimension. So what is the formula? It is input plus kernel minus 1. So what is input? Input is 2. And what is the kernel size? It is kernel is also 2 cross 2. So 2. So 2 plus 2 minus 1 will be 3. This is for height and this is for width. So you are getting 3 cross 3. Now from input image 2 cross 2, we are increasing to 3 cross 3. Now let us understand what is the math, how the calculation is going to happen. We know that ultimately the output is 3 cross 3. So which means in all of these positions you will have this 0. Now you have to multiply, input should be multiplied with the kernel. What is input? 1. 1 is multiplied with all of these values. So since the position of 1 is here on the top left, so 1 into, you will have the values. So you will have, so these 4 values will be replaced it with, you can see 1 into 4 is 4, then 1 into 3 is 3, 1 into 2 is 2, and 1 into 1 is 1. So what is this 1? 1 is input. What is 4, 3, 2, 1? It is kernel. So this is the value that we have obtained, which is G1. Similar way, you take the second input 2, that is getting multiplied with. So initially it will be all zeros. So since 2 is in the top right, so top right 4 positions are all zeros. So when 2 gets multiplied, 4 into 8, 6, then 2 into 2, 4, 2 with 1 is 2. So this is what is G2. Similar way you do it for the third input multiplied with the kernel and the fourth input multiplied with the kernel. So this is what you are going to multiply, and towards the end the transpose convolution is, you have got 4 different matrix. Combine all of those. How is that you will do? You will just perform an addition. So how is that you do? This is G1, this is G2, this is G3 and G4, and what is that you are doing? It is a 4 plus 0 plus 0 plus 0 is 4. Then 3 plus 8 plus 0 plus 0 is 11. 0, 6, 0, 0 is 6. Respective positions you will do the addition. It is 2. Similar way, 1, 4, 0, 4 is 9. So on so forth, you will do an element wise addition in each of these matrix, and you have obtained the transpose convolution. Okay, now here there is something to learn, right? What is there to learn? Kernel is there. Definitely initially the kernel values will be some random values. Over a period of time in the back propagation you are going to update these kernel values. Okay, so which means from 2 cross 2 you have increased to 3 cross 3, which means you have upsampled it. So definitely better than the previous upsampling, right, where you have just copied the values. This you have performed some operation, but there is one drawback here. What is the drawback? If you observe here, there is a kind of a problem that you can observe in this matrix. What is that problem? Can you see here? There are some values which are very large. There are some values which are very, very small, right? So what is this problem called? It is called a checkerboard problem. What is this checkerboard problem? You can visualize this in the diagram. You can see there are some grid kind of texture that you can able to see in the image, where you have an box or alternative bright or dark pixels or a square pattern. Can you able to see uneven texture? You can able to see something like this as an output if you go for transposed convolution. And what is this problem? This is called a checkerboard problem, and this checkerboard problem has occurred because of uneven movement of the kernel onto this input image. So for some part of an input image you are applying kernel again, for some part of an input image you are applying kernel only once. So because of this you are able to see some square kind of a pattern. That is the problem with the transposed convolution. So which means although transposed convolution is increasing the dimension, but we are facing this checkerboard problem. This is not intentional, it is not any noise which has occurred, it is the concept itself will create there is a systematic artifacts which has occurred because of the operation itself, not any noise or an external noise that is being added. No. How do you overcome this? So first, whatever is the input, perform an upsampling. How do you perform an upsampling? We can use either zeros, or you can go for nearest neighbor, zero insertion or nearest neighbor. So we have used nearest neighbor. First perform upsampling, then perform a convolution operation. So what is that we have done? First upsampling. Well, how is that we have done upsampling? This is 2 cross 2. Upscaling sampling factor is 2. Therefore, we have got 4 cross 4. So this is upsampling method. For this you are applying a convolution method. So what is convolution? Same as your previous one. You will take the kernel and you will multiply, you will apply it onto a matrix and then perform a calculation. So what is that first you will do? You will take this 2 cross 2 and you will take the entire kernel and then perform an operation. So how is that you are doing it? You can see. So it is 1 getting multiplied with this, then 1 getting multiplied with this, then this 1 is multiplied with this, and this element wise you are performing a multiplication, and then you calculate and then get the result and store it as an output. Next, slide it. You will take this part. This is the next part. So this is what is, and then you will take the same kernel, perform element wise multiplication, and then this is 1 with this, 2 with this, then 1 with the 2 and 2 with 1. So you are performing element wise and then you are getting a result and then you are storing it here. Similar way, now when you scale you are going to slide when you get this matrix. So you will take and then perform the same operation, and so on you will be able to get the values. So once you complete, when you stride, you take this matrix, then you take this, then you take this. Again when you stride down, you take this part, then you take this part, then you will take this part. Is it not systematically you have gone through the entire matrix here? So upsampling first spreads the values uniformly, and the subsequent convolution when it is applied, you are applying a kernel evenly. So this avoids an uneven overlap, so that here you will avoid that checkerboard artifacts. So if you see here for the same input 1 2 0 1 and then the same kernel 4 3 2 1, the matrix that you have obtained is this 4 11 6 2 9 5 0 2 1, and the same when you have performed upsampling and then when you have used the see the input is the same 1 2 0 1, here the input is the same, and kernel 4 3 2 1. When you perform, you are seeing that there is an even distribution, not some values are very small, some values are very large, no. So this is the concept that is used for in autoencoders. We first go for upsampling and then go for a convolution. You can see Now what we are discussing is the decoder part. In the decoder part, whatever the latent space is passed as an input. So the latent which is obtained from our previous one, that is first you are doing an upsampling. Upsampling, what is the factor? It is 2 cross 2. So now first you will increase it. So when you increase, definitely if it is 7 cross 7, it will be increased to 14 cross 14. Right. So because 7 cross 7, when you take a scaling factor as 2, it is 14 cross 14. So that's what is a 14 cross 14. First you are upsampling it, then you are performing a convolution operation. So convolution, 128 such kernels are there. So whatever is this 256, when you perform an deconvolution operation, you are going to get from this the output of this will be 14 cross 14 with 128, because there are 128 such kernels. Right. So this is what we have seen it. So next, the output of this is, just see only so much, 14 is changed to 7 is changed to 14 cross 14, but the number of kernels that will remain the same. But when this is passed as an input to this convolution operation, the output what you get is 14 cross 14 with these many number of kernels, 128. That's what is this value. Now again you are performing an upsampling. Upsampling again, when you perform, because the scaling factor is 2, 14 cross 14 will now be converted to 28 cross 28. So 14 is changed to 28, and next you are applying it to a convolution which is having 64. So it will be 28 cross 28 cross 64. This is the output that we have obtained, and you are using the last convolution layer. And why do we require a last convolutional layer? Because you see here the dimension is 28 28 1, but here it is 28 28 64. So now it should go back to 28 28 1. So go for one kernel. The kernel size is 3 cross 3, padding same, and then the output of the previous one will be passed as an input, and then you are getting a reconstruction data back, so which we have obtained as 28 cross 28 1. Since it is an output, we have used sigmoid as an activation function. Why sigmoid? Because here the input we have in terms of zeros and ones. Because it's a binary, the data is in terms of 0 and 1. Definitely even at an output layer, the data should be in terms of zeros and ones. Therefore, the activation function used is a sigmoid. So you will be seeing this in a hands-on session also, but I am trying to explain you how when an image is passed as an input to an convolution, how autoencoder will extract the features, from features how it is going to reconstruct. So here the input what we have considered is this, and then towards the end of autoencoder function, we are going to get a latent output and then a reconstructed output. So we are going to get these, and you can able to plot to visualize the results as well. So this is what is CNN based autoencoders, where input is an image. Therefore encoder will have an CNN base, that is convolution and pooling, and the decoder will have upsampling and convolution. So this is what is, and the sigmoid, as I said, we are using a sigmoid here because the input features are in terms of binary. Ultimately at a reconstruction the output also should be in binary. Therefore we are using a sigmoid as an activation function. Now this is important concept to be remembered. Now the latent space is an hyperparameter, right? So how much dimension you want to reduce it, that you will be in the code itself, you will be mentioning it. If you have a smaller number, so what is going to happen if you have a smaller number? Is it not you are compressing information so much that you know, the information, important information you have compromised because you are reducing too much, and with that compromised latent space, when you reconstruct back, definitely the reconstructed image will not be very good. So it will be too much of blur when you have a smaller latent space. So you will have a lot of blurriness. But at the same time, if you increase the latent space, but not as much as the size of the original input, no. If the dimension of an latent space is increased by a little larger number, definitely the compressed information is very good. With this, the reconstructed one is also very good. You will get the reconstructed image quality also very good. But just because we get a very good reconstructed one by having a larger dimension, if you increase it beyond a certain limit, you will start getting the diminishing results. You will start getting a lower quality images. So therefore, this is an hyperparameter, and the latent space dimensionality will actually control what should be the reconstruction quality. So the smaller, poor, larger, it is good, but just because larger is good, if you go for higher and higher number, then the quality of the image starts deteriorating. So from this you should know, you cannot go for very smaller value, nor you can go for larger. You can fine tune the parameter here. So this is all about the CNN based autoencoder. Let us see two simple other autoencoders. One is a shallow autoencoder. So what is a shallow autoencoder? The word itself says shallow. This is where you have just one hidden layer. So when you just have one hidden layer, how does the architecture looks? You have an input layer. Input layer is passed to an hidden layer. The output of that hidden layer itself is the latent representation, that is then passed to an output layer. So you just have only one hidden layer between input and output. So let us see one example here. So here the input is 784. So ultimately you want output also 784. Between input and output there is only one hidden layer, and that hidden layer is a hidden layer having 32 neurons. So when 784 is passed to an hidden layer which is having a 32, the output will be 32. This 32 should be passed now to a layer, because ultimately you should now pass to an output layer which should give you 784. So at an output layer you are passing 784 neurons. So let us understand that. Input is 784, that is passed to an hidden layer. Input is 784, hidden layer is having 32 neurons, and activation function is ReLU. So therefore encoded output will be having 32, that is passed as an input now. So 32 is passed as an input to this. How many neurons you should have? 784. Why 784? Because it is a shallow, where after hidden layer that is an output layer. So at the end of an output layer you have to get 784. If you have to get 784, then you have to pass these many number of neurons. And what activation function we are using? Sigmoid. Why sigmoid we have to use? Because ultimately if our input is in terms of binary, then the output also should be in terms of binary. Therefore the activation function what is used is sigmoid. Now, what if our input is some numbers, but see during our pre-processing, what if you have scaled down the values between 0 and 1? We have normalizing the data, right? When we scale down the value between 0 and 1, then ultimately the output also should be in terms of 0, 1. Then we will be using a sigmoid. So at the output, at the decoder output, the reconstructed value should match the range of an input data. Suppose if a pre-processing scales the features to 0, 1, then obviously sigmoid is an activation function that you should use at an output layer, and so that it will scale down. And what should be the loss function? Definitely binary cross entropy should be the loss. Suppose you have features where you have not scaled the values between 0 and 1, you are using a real valued only. If you are using real valued or a standardization method, then use a linear activation. Here it should be a linear activation, and the loss function will be a mean square error loss. So what is the shallow? Shallow autoencoder is the one where we just have only one hidden layer between input and output. Next, we have deep autoencoder. What is deep autoencoder? The name itself suggests you just don't have one hidden layer, you have multiple hidden layers. So when you have multiple hidden layers, how does it work? Definitely you should go in the decreasing order at an encoder side, and you should go in the increasing order at the decoder side. The output of last decoder will be the latent space. Latent space is passed as an input to the decoder. So you see, input is 784, output is 784, which is first passed to an hidden layer which is having 128, that is then passed to a next hidden layer which is having 64, which is then passed to a next hidden layer which is having 32. Since it is the last layer, the output of that will be the latent. Since it is 32, 32 will be the output. That is then passed to an decoder which is having 64, then 128, then it is 784. Output of this will be a 784 values. So let us see how we have coded that. 784 is passed as an input, that is first passed to a first hidden layer H1 which is having 128. So 128 activation ReLU. So that is given to X. Now that is passed as an input to the next which is having the 64. So 64, that X is passed, you are again storing the value back in X. That is again given to a decoder which encoder which is having 32. So 32. Now this X is passed, and whatever output you are getting will be a latent representation. Now this latent representation is passed as an input to a decoder which is having 64. So latent decoder having 64. Then that is passed to an next decoder hidden layer which is having 128. That is then passed to this is the last layer which should have 784. Last layer 784, and sigmoid same, if you have scaled down the values between 0 and 1, then use a sigmoid, or if you have used standardization where you have not scaled the values where it is a real valued, then use a linear activation function. So this is what is deep autoencoder. Now can you think of this? Can I use a deep autoencoder architecture for an images? We have seen some time back for an image we have to use for CNN based autoencoder. What will happen if I use deep learning, a deep autoencoder? What is deep autoencoder? If you take this 784, this is 28 cross 28 cross 1, which is the image which is having 28 to 28. You are converting that into a single vector of size 784. Now, so the input which is having 28, 28, you have converted into a single vector, and then you have passed it to a deep autoencoder. Can we use this for an image? What is the answer? Definitely answer is no. Why? Because the minute you have converted that into this, the spatial information is lost. When spatial information is lost, look at this. This is an output of a deep autoencoder. This is the output of CNN autoencoder. Can you look at wherever I have highlighted it with red? Can you look at this part under this? So here can you see the features are more sharp here, whereas you have lost the information there. And similar way, can you able to see this image and this image? Can you able to see there is something that is there on the t-shirt, but that is not being captured here properly. Similar way you can see this example and this example. Why all this is happening is because here you have flattened the image. 28 cross 28 you have reduced, when you have flattened it, you are getting a 784. So because of this, it is failing to preserve the spatial relationship. The edges, contours, shapes are being lost when you use a deep autoencoder. Whereas if you use a CNN, definitely because your convolution, the local spatial structures are preserved, and then it learns the edges, textures and different shapes. And decoder are using the learned feature maps, you can able to reconstruct the image properly. Therefore, whenever we are dealing with an image as an input, it is always advisable to go for CNN based autoencoder. If you have a tabulated data, you can go for either shallow or you can go for a deep autoencoders. With this, we have come to an end of this particular session. In this session, we have seen the different types of autoencoders, and in this we have started with CNN based autoencoder, then we have seen an shallow and then deep autoencoders, and in the upcoming session we will see something called as an regularization techniques in autoencoder. So there can be an high chances of overfitting a problem here. If there is an overfitting problem, what are different regularization techniques that we will be using in autoencoder? So you can recall the concepts. The various regularization techniques what we have already seen in our deep learning course. We have seen L1, L2 regularization, we have seen dropouts, we have seen early stopping, then we have something called as a batch normalization if you are dealing with an images. So all these are already the regularization techniques. So can we use those regularization techniques, or do we have any other special regularization techniques for autoencoder? So that is the point of discussion for our next session. Thank you.